I'm going to turn it over to Kay Smalley to introduce our speaker. Thank you.
Well, what you can see on your screen, if you are looking at the screen, is that our speaker is Theodore Van Aken, who is superintendent of the Water Reclamation Facility here in Holland. Theo has a degree from Michigan State in Biosystems Engineering, and he's been with the Holland BPW for approximately 8 years. He's led a number of projects and managed them while he's been at BPW. He's also gotten a certification as a wastewater treatment operator. He is currently as the superintendent of the reclamation facility. He is involved in planning and overseeing the addition of a biodigester to the treatment plant, to the reclamation facility. I got to get this straight. I'm a fairly recent immigrant to the state of Michigan, and in Emporia, Kansas, where I came from, we always said it was a sewage treatment plant, and I'm trying to learn the proper terms. It is a nicer way to say it, and it is also, I think, what Theo is going to explain to us as he talks today is why you emphasize water reclamation facility, because of the number of things that this facility does to clean up the water so that we have a better, cleaner water going out, than a lot cleaner water going out than we do going in. So with that, I'll turn it over to Theo, and he can tell us what he wants to tell us.
Well, thank you, Kay, and thank you, Susan, for inviting me to come talk to you all today, and thank you for your interest. As Susan said, I am certainly willing to entertain questions as they come through. So I have multiple screens. So I have all of you up on one screen and my presentation on another. So I'll try and keep an eye out, but feel free to speak up. You know, I've got a lot of information to present today, and some of it may be more interesting than other bits. So I certainly want to help tailor the presentation to help your interests. So as Kay did point out, we are a water reclamation facility, and that is a fairly recent name change. A couple years ago, we were the Holland Wastewater Treatment Plant for many, many years. You know, at one point, we were the Holland Sewage Treatment Plant, you know, many, many years ago. And the first part of my presentation is really going through the history of the water reclamation facility. And a lot of that does include the difference in opinions and what we're doing and why we're doing it, you know, because really our purpose here is to treat whatever wastewater comes from the surrounding region, and we want to make that clean water. We want to be able to, you know, make it so we can all exist in the environment without damaging it. So that's really what we're doing, and we're trying to reclaim this water. We're not a disposal site, you know. Everything we do is getting it ready for its next use. We do have a fairly long history here in Holland. This screen shows our early years. You know, there were public sewers installed in the city of Holland all the way back in 1901. And that's really very forward thinking for a city of this size. You know, at that point in time, people were really just kind of coming around to believe that there's issues, you know, with microbes and sewers and things like that. So, you know, rather than having a bunch of open cesspits or septic tanks, which were the norm, you know, back in the day, we installed sewers to at least get the sewage away from where the people live and get it out into the lake. In 1927, we added on our first actual treatment process, and continuing forward in 1934, we added some odor control. 1962, that's when we really started to build the wastewater treatment plant as you see it today. And in 1972 is when the Clean Water Act was passed, and that really has guided the development of the water reclamation facility from that point on. So on the screen in front of you, you'll see a map of the original public sewer system from way back when, in around 1901. And we actually had 4 different discharge points into Lake Makatawa. The 2 main ones are shown on this drawing. There's a red arrow at 12th Street outfall. And then there's another outfall that goes right down central, actually where our site is located currently. It may not sound like it, but this was really a big step, because to keep people from getting sick, you need to get the sewage and the pathogens away from them. And that's what this allowed, and it allowed our city to grow without having major cholera outbreaks or diphtheria and other human pathogens such as that. We did have septic tanks on those two main discharge points. So there was some treatment, but I don't know I'd even call it that, because we also had industry back in the day, tanneries and canneries especially, that had a lot of wastewater. So those septic tanks may have caught some solids, but really the stuff going into Lake Macatawa probably wasn't so nice. But given there were a lot less people back then, so the lake could actually accept more pollution than it can today with the development that's gone on since then. Well, in 1927, on the site where we're located currently, an Imhoff tank was built. And the picture of the Imhoff tank is here on the right side of the screen. That was taken not too long after it was built. And kind of to help you orient where this picture is, this is on, and I'll have some further pictures coming soon that will show where this is located, but you're actually standing on the west side of the tank, looking due east, more or less towards like window on the waterfront. So you can see there's a couple of houses and a church visible in the background. The Imhoff tank was a treatment process that allowed, it's kind of like a septic tank, but it also would anaerobically digest the solids that fell to the bottom. So the left is a cutaway of that. So it's just something that allows settling to happen. Not a lot of treatment, but certainly better than what we had prior to that with the septic tanks. And we've always and still are very concerned with odor at our site. We're very close to the city of Holland. Even back in those days we were, there's houses all throughout the site where we're at currently. So we did build an odor control system as far back as 1934. And really what this odor control system did was it burned the gas that came off of the Imhoff tanks, the digestion that happened at the bottom. It's a methane-rich gas that comes off and it smells fairly bad. So the picture is actually showing a pumping station as a building on the left, and on the right is a small incinerator. You can see the smokestack, and that is what was burning the gas to help reduce odors at our site. So our next big step from 1934 up until 1962, the city continued to grow as we needed to build more of like a true treatment works. And this is where you start to see these are structures that are still in use today. In 1962, we added primary treatment to our facility. Here we're looking off to the northeast, over kind of across the wetland there to the north of the plant. The building in the background at the time housed an anaerobic digester, and that's what the two round tanks are. So in the forefront, we see a primary clarifier. The primary clarifiers are, a good first treatment step, and they can actually treat about 40% of our pollutants that come into us. So the Imhoff tanks also were still being used at this time, but they were being used to disinfect the wastewater as it left the site to help reduce any chance of pathogen spread. So now we start to get into the secondary treatment. These are improvements that have come around mostly from the Clean Water Act at this point going forward. So primary treatment is easy. It gets a fair amount of your pollutants out, but the water that comes off is still pretty gray, pretty smelly. The secondary treatment process is what allows us to get to what I like to call nice, clean, clear water that can be safely discharged into a lake, such as Lake Macatawa. So to do that, we have to add aeration to feed bacteria to break down pollutants. And then we have to add secondary clarification steps that allow the pollutants and the bacteria to settle down to the bottom of the tank. We'll dive into that when we go through the plant processes a bit more in depth, but these structures are all still in use today as well. We did add some new solids handling equipment for dealing with the biosolids that come off. And then you can see on the north side, that's the window on the waterfront park now, but back in those days, it was used as a dump. So there's a lot of work going on over there. So really from 1980 until today is when the plant, as we see it now, really came into being. So we expanded to a regional facility in 1980. In 1992, we added a true odor control system. We had some odor issues back in those days. We also covered tanks. We also had a very successful program going from 1992 to 2017 of reusing our effluent for the James Young coal-fired plant. 1996, we did a major expansion to increase our capacity to be able to treat an average of 12 million gallons per day of incoming sewage. In 2011, we added a Headworks facility that I'll review as we go through. And then in 2015, we revamped our plant to expand biological treatment capacity in our secondary treatment, as well as added solids handling capacity, which brings us to the current project we're working on today, which is the anaerobic digester that I'll touch on later in the presentation. So 1980, not only the city of Holland continued to grow, but the townships were seeing excessive growth, or not excessive, I should say, but they were seeing a lot of growth on the north side of the river. So you had Holland Township, Park Township. We need to do something with their sewage. So the plant was expanded and we added flow from the north side, which comes across the river, and it comes to our facility for treatment. So we are now not just treating the sewage from the city of Holland, but we're doing Fillmore Township, Lake Town Township, Holland Township, Park Township, and up until recently, Zeeland Township all came here to our facility for treatment. The west plant, which is where I'm physically sitting right now, which is on the west side of River Avenue, was built as a high purity oxygen activated sludge process. And this uses, rather than ambient air to provide oxygen to bacteria and microorganisms, we use a refined oxygen product because that's all that the microorganisms really need. So it allows you to treat more in less space. We added a new administration building. So my office that I'm sitting in currently was added. We added a new maintenance shop. So the plant got a lot bigger at this point, 8.5 million gallons per day average. In the early 90s, we were suffering from some odor concerns in the area. So you'll note from the last photo to the next plant photo, you see that we covered a lot of our tanks and we added this chemical scrubbing odor control system, which basically uses a countercurrent bed of media where odorous air is drawn up through the media, and then we spray like a sodium hypochlorite solution down on them onto this media, and it precipitates out the sulfur compounds, which are a major odor. But you can see here I have for those that are interested, we have the process of the chemical reaction that takes the odor from hydrogen sulfide into sodium sulfate, which gets it out of the air, which makes it so it doesn't smell. In 92, this was actually very forward-thinking thought on my predecessor's part. We're discharging all of our water from our site into Lake Macatawa. Well, why not utilize that water, which is very clean, and in many cases cleaner than what's in Lake Macatawa, and use it for cooling water at the James Young power plant. Coal-fired process uses a lot of cooling water. So by discharging our effluent directly into JDY's influent, it allowed them to have a cleaner cooling water. They didn't have nearly as much plugging of their heat exchangers. And for us, we didn't have to worry about removing the chlorine from the effluent. So it was a win-win situation. The new Holland Energy Park was built and James Young was retired at 2017. So that meant that we had to take on some more duties than what we were before that. Our last real major expansion was in 96. As I said, that's when we brought ourselves up to our current capacity. So we currently have the ability to treat on average 12 million gallons per day of sewage coming to us. So the way we got to that 96 is you can look on the west side, and we actually expanded. There's more reactors there, and there's 2 more secondary clarifiers. That was the big change we did. We added some more aeration to the east plant as well, the part of the plant, the east side of River Avenue. So we added some holding tanks for our solids as they're produced, and then we expanded our odor control system. Now, in 2011, we added a Headworks facility, which I'll go into in a little more depth further down the line. But what Headworks does is it screens your incoming sewage flows to try and get inorganic particles removed. So that can be sand, that can be gravel, it could be boards, toy cars. I mean, just whatever finds its way into the sewer makes its way to us. So that's what this is for. We didn't have a very good Headworks before this. So that meant we had a lot of pumps that would plug up, a lot of mixers that would get covered in on rags and different things like that. So that's what this was here to help us with. So in 2015, 2016, this picture really looks very similar to the 1996 expansion, but the main changes that we did, we converted the plant side of the plant, the east side, on the east side of River Avenue, to high purity oxygen, as well as the west side. So that allows us to get 30% more of our secondary treatment in the same amount of tank space. For those that are familiar with our location, we are pretty constricted as to where we can continue to grow. We replaced our dewatering, our sludge processing equipment. We replaced our odor control system with a system that was the same to help keep that going for us. And really that gets us up to the project today where we're working on the anaerobic digester. And I have a section that really dives into that. But I thought I wanted to, before we do that, we should really touch on how do we treat the sewage coming to us in the water reclamation facility. And that's what this portion of the presentation is going to focus on. So our inputs, we're put here, we're connected to the sewer system, and we get domestic sewage, like what comes from a household or an apartment building. That's your normal toilet, shower, sink, drainings. We also have commercial wastewater, so that could be a car wash, a larger store like, a Walmart or a Meijer coming to us. Industrial wastewater, which is, always can be very concerning because some industrial processes have some pretty nasty waste that comes from them. So I'll jump into that here in a little bit, how we manage those. And we also have to deal with infiltration and inflow. And infiltration and inflow is more or less clean water that leaks into the sewer system through, if it could be, like right now we have very high groundwater levels. If there were loose joints in pipes underground or in manholes, it will leak in through those and it will dilute the wastewater and come to us. Also, there are many houses, and especially on the city of Holland itself, that were built in a previous era where sump pumps were often hooked up to the sanitary sewer line. One sump pump can pump over 200,000 gallons of stormwater, basically clean water, into the sanitary sewage system in one day. So it has a really big impact on what we do here, and really kind of limit some of the treatment just due to the volume that comes at us during rainstorms. We are a separated sewer system. So that means that our storm sewers are separate from our sanitary sewers. And that is a very helpful thing. That's why we don't have the same issues that Detroit or Grand Rapids or Lansing have had to deal with, where every time it rains, the wastewater overflows. That doesn't happen for us, but it definitely does spike up during rainstorms. Our outputs are really two things. We have the clean water that we've reclaimed. We pulled all the pollutants out of it, and that's ready to go out. And then we have the biosolids, which is a big part of what we're doing right now with this new anaerobic digester project. So I wanted to see if I can successfully switch my screen for just a second to show for those of you. I imagine most of you are aware of our current location, but for any of you that are not, we sit here kind of near the Unity Bridge on River Avenue going up to Holland Township. So I will zoom out a couple so you can see where we're at. But this is, you can see the Jamestown plant. This is on Google Maps, so it's a couple years old. And the coal pile is gone. Downtown is here on the south side of it. But as I zoom in, you'll see between basically Central Avenue comes up to 3rd Street and then to 1st Street. Our facility exists here in between these areas. So we've got water on, the one side of us, and then the city is kind of encroaching on us from the other side. You'll see between Pine and River Avenue, between 1st and 2nd Street, that is our west plant. And then on the east side of River Avenue, between 1st Street and 3rd Street, that's our east plant. This is always something that's irritating to me about Google, is they actually show Central Avenue and 1st Street continuing through our site, and they actually don't. At one point in time, many, many years ago it did, but technically this is all a private site, or I should say municipal site, that we limit access to just due to safety concerns. So Let me switch the screen back to where we were. All right, so this is my PSA that I always have to throw out there for anyone with the wastewater treatment process is what kind of risks do we see here? And one of the biggest risks that have come out in the current years are the eponymous wipes here, the flushable wipes. So I like to circle flushable. And flushable wipes do flush down your toilet. They do make it, generally, as long as you have a newer home with decent plumbing, it will make it out of your house. But you combine that with kitchen grease, hair, all kinds of other nasty stuff. When it hits that sewer, it all congeals and you end up with this. This is not Holland. This is actually a picture taken from London, England. But this was they called it the Fat Bird. And it was about the size of a city bus that plugged up one of their sewers. So, and these poor sewer workers have to go in there like this gentleman here. I believe it's a gentleman, at least it could be a woman, I'm not sure. Have to dig it out by hand. Same thing happens here in Holland, just on a much smaller scale. We have crews that spend, many hours a week jetting out sewers, trying to clean them out just to keep the wastewater coming to us. And even when it hits our facility, we still run into issues here as well. It plugs things up, it's dirty, it smells bad. So please, just take note, be very careful about what you do flush down the toilet, sending into the collection system, because it can have a huge impact on, expenses and safety too, because if it's not safe only for the worker to go in there, but when the sewer does plug, it will cause the sewage to back up and it could overflow manholes. It could even overflow in your basement, which none of us want to happen. It's happened to me at home before, and it's really not a great day. So grandstanding and soapbox aside, I wanted to review with you this is our guidelines for the water reclamation facility that we have worked out with the state of Michigan, the Department of Environment, Great Lakes and Energy, previously the Department of Environmental Quality. They dictate what we can discharge on the clean water side, and they dictate what we can put out there on the biosolids side. These rules are promulgated by the Environmental Protection Agency, and EGLE takes them and they help craft them into permits for all of us. So we have one, any city that discharges in larger industrial sites that discharge wastewater to surface water or groundwater, they have to have one of these National Pollutant Discharge Elimination System permits, or as we call them, the NPDES. And this is put together with EGLE. They go through and they have a mass balance spreadsheets. We look at lake temperatures, influent, effluent temperatures, and they give limits to facilities such as ours that ensure that when they discharge their wastewater, their clarified and cleaned wastewater, that we're not going to have a negative impact on our receiving waters, which for us is Lake Macatawa, right by the James Young, just on the north side of the James Young power plant is where we discharge. So you'll look through here and you'll see some of these are there's different limits from summer to winter. And that really has to deal with based on water temperature, the lake can actually handle different amounts of pollutants different times of the year. So you'll see that during the summer, the water is hotter, henceforth our limits are more strict. And these limits, we're always trying to stay underneath. So I'm going to look, you'll see a few different things in here, like a flow, for example, we only have to report it on a monthly and a daily limit. So that's why it says report. There's actually no limit on the flow that we can take in. We don't really have control over that, but we just have to be able to treat it. So as we go down the permit, you'll see we have carbonaceous biological oxygen demand, total suspended solids, ammonia, nitrogen, phosphorus. Those are our compatible pollutants that we can treat for here at our site. We don't have ammonia treatment currently, but we are looking to add that as part of the anaerobic digester project. Carbonaceous biological oxygen demand is it's a measurement of how much oxygen is needed. So if we dump something like a high strength waste with a lot of BOD into Lake Macatawa, that will break down. So we're breaking it down for the lake before it gets there. But if it were to go straight into the lake, It needs oxygen in order for the microorganisms to do their work. So BOD, they take that oxygen out of the water in the lake, and that causes the dissolved oxygen levels of the lake to go down, which causes fish kills and other issues. That's what BOD is all about. Suspended solids are just what you think they are. It's just solids, you know, and so it can cause the water to be dirty. You know, it can harbor pathogens. It also can harbor a lot of phosphorus as well. You know, ammonia can be toxic at high levels in any, whether it's wastewater or not. So that's why we keep an eye on our ammonia and have limits there. And then phosphorus, obviously, there's many issues in the Macatawa watershed with phosphorus loading and causing algal blooms. So we want to keep that limited as much as we can. Other things we track are fecal coliform bacteria. So we check that every day to make sure what we're sending out doesn't harbor any pathogens potentially. We do use chlorine to disinfect. So we have to ensure that we actually are staying under the limit for chlorine because we want to make sure that we're not poisoning the lake with that. We check cyanide. We do check PFOS, PFOS, and PFOA, PFOA on a quarterly basis. And then let's see here. We also do mercury. That's a huge one for us. We have to do a certain amount of our total solids have to be removed. We want our pH to be a nice neutral number between 6 and 9. And then dissolved oxygen has to be a minimum of 5. So those are all the things that I look at every day. We look at our treatment process, all of our operators here, to ensure that we meet the terms of this permit at all times to keep Lake Macatawa healthy and safe. So the collection system has grown a lot since that initial picture I showed you from the early 1900s. This is only our south side. So this is a picture taken from a program that we have called a GIS, or the Geographic Information System, showing, I couldn't honestly get all of it in there. It does go a little further south than what I could put on this slide. But you could almost mirror that to what's on the north side. Holland Township manages their sewer collection system. That's why I don't have as readily available map of it. But they range all the way as far north as Target, I believe, and they go all the way out to the lake as well. So we have quite a few miles. I think 200 some miles of sewer mains that come to here. And we have pumping stations along the way. So if we get to a point where it flows by gravity only so long, you pump it and then it flows down to us again. So our site is kind of right there at the very end of Lake Macatawa, you see, and that's where it all comes to us. So, for the plant, we could treat the wastewater here, but also a big part of what we need to do is make sure that what comes to us can be treated. And we do that through the industrial pretreatment program. And I was commenting to Kay earlier, but this is the same department that's working with Hope College on their COVID-19 sewage testing. So what this crew's job is, they have 2 technicians, 1 supervisor, and then I do a bit of the management there as well, is we're working on monitoring what's coming down the sewer to the water reclamation facility through the collection system. The biggest thing that we're doing is working with our major sources of wastewater. So that's going to be your industrial customers, and that's going to, especially food processors, chemical facilities. You have to keep a close eye on chrome plating for metals. We actually have, we know all of these, organizations in our collection system area. They know us. Most of them actually have permits that we issue to them saying what they can discharge to us, very similar to that permit I showed you earlier, but it's not an NPD, yes. So we sample them on a monthly basis. Some are sampled quarterly, some are monthly, some are multiple times a month. And we're tracking those compatible pollutants. So that's your biological oxygen demand, your phosphorus, your total solids, your ammonia. Then we're also looking into what we call the incompatibles or the toxic pollutants. And those are pollutants that we don't really treat for at the water reclamation facility. There's a lot of these out there. The biggest ones we deal with are heavy metals, benzenes. So just want to throw a couple examples out there. And really the way to keep those toxic incompatible pollutants out of the wastewater treatment process is to regulate the waste coming to us from the industrial customers. So We sample them, as I said, using these samplers in the picture here. So the picture on the left is showing a sampler. It's all wrapped up and it's ready to go into a manhole. The picture on the right is that same sampler disassembled in the back of one of our trucks. This sampler can be discreet. You know, we don't generally tell people when we're sampling them. We want to make sure that we're getting a realistic snapshot of what their sewage is coming to us, because we don't have time. We can't sample every customer every day, unfortunately. There's just not enough time and not enough money is the real big thing for that. So this sampler actually hangs down underneath the manhole cover, and there is it's wrapped around the sampler on the left and on the right. There's a clear plastic hose with a metal tip on it. That hose gets dumped down into the sewer as the wastewater comes by. And then the head of the sampler, which if you look on the right, the picture on the right, and it's the leftmost portion, it says GLS on it. That houses a computer and a pump. And ever so many, if we have a flow meter, we can hook it to a flow meter and we pull a sample every so many gallons, which is the preferred way. But if we don't, we just have it pull a sample every so many minutes. So it will draw a sample up through the plastic hose and it will discharge it into this plastic carboy that you see in the center of that right-hand photograph. Then every day, our guys go out there, they pack that thing with ice to keep it cool, and they grab samples out of these and they bring it to our lab. And we also use contract laboratories as well to do that work. So same process goes with the COVID sampling. Sorry to switch back so quick, but you know, Hope College has actually worked with our department. They purchased several of these, so they're doing it throughout their collection system to help keep the tabs on the COVID prevalence in their student body. So after we have the collection system, everything has come to us. We are at the plant now. So everything's in, it's here, it's ready to be treated. We have our first step is a preliminary treatment, or the headworks, which you saw in our historical files. The headworks really is two different parts. We have bar screening and grit and sand removal. The bar screen, there's a picture of one on this. It's that lower photograph. And the sewage actually flows through the screen and the large parts catch on the bars. There are rakes that go down and they scrape the screen up. So it's at an angle and they scrape up all the solids and then they discharge them into a dumpster, which then goes to a landfill. The next step after that is the grit and sand removal, which is a vortex system. There's an upper right-hand corner of the slide shows a cutaway of that. And basically what it is from the upper left of that cutaway, the water comes in, it spins around the cyclone in a circle, and all the heavy portions, which would be your gravel, rocks, and other such things, move to the center and drop down as their velocity slows in the center of the vortex. We pump those out and they go to the landfill along with the screenings. The next slide shows a layout of what that actually looks like in person. And I wish I could have all of you at our site because I'm much better at describing this when I can point at them. But inside of the building, we have two screens. So the sewage comes to us from the north and the south side, and then it goes through the bar screens, and then it goes to the vortex grit chamber. Then it moves on to the next step, which is the primary treatment. And that primary treatment was a step that we added back in 1962. This slide here shows us a cutaway of what the inside of a primary clarifier looks like. And to be honest, this is the same for the secondary clarifiers. We want to make things in the wastewater world, try and keep it simple. You know, we don't want it to get too complex, too many different machines. You know, after our headworks, we actually flow by gravity through the rest of the plant for the liquid portion of it. And gravity is our friend, especially in primary treatment, because that primary clarifier is nothing than a big, wide spot in the line that allows the water to sit in there for several hours. And as that sewage sits in there, it will stratify, and you'll have all of the grease, fats and oils that come down the sewer to us will float to the top. All of the heavy pieces will all sink to the bottom. This rake shown in the screen here spins at a very slow rate. You know, it takes it a couple minutes or more to do a revolution. And that's collecting all of the heavy solids into the center of the tank where we pump them out to our solids handling process. And all the fats, oils, and greases are skimmed off of the top. And then right now they're going into a landfill, but once our digester's in, we'll be able to digest those. So with primary treatment, you can get, I always say a rule of thumb is about 40% of the treatment done. So when we come off the primary clarifiers, it does smell funny. It's still gray water, but it's not as putrid as it was if it was just raw sewage and you let it sit. So this is also the part where we do our phosphorus treatment. And our phosphorus treatment is done by adding ferric chloride, which is in a liquid form. It's a chemical that is added to this raw mix deck with the effluent from the Headworks process. That ferric chloride binds to the phosphorus and it causes it to flocculate together with those heavy solids that sink down to the bottom. So this is, if we have more phosphorus coming in, we just turn up the ferric chloride and it draws it out. So it's fairly straightforward and easy to treat for phosphorus. It's just very expensive. So it is really nice. And that's why we work with our customers to limit the phosphorus that comes into our site. So after primary treatment, we are going to split. So all of our primary clarifiers are part of our East plant. They were part of the first, iteration that was built back in the 60s and early 70s. After the primary, it will split to our East and West plants for secondary treatment. And the secondary treatment process is the same overall process on both sides of our facility. And what that process is that we are adding oxygen, in this case, high purity oxygen, into the primary effluent, and that feeds microorganisms, mostly bacteria. There's some little protozoans you can see in there, and they do their job and they break down the pollutants. So they're eating up the organic pollutants, especially the biological oxygen demand. So by mixing it well and adding the oxygen, we're going to do all the work that would normally happen out in the lake. This is under a controlled environment, and that way we know that we can knock those numbers down before the water is discharged. After it goes through the bioreactor aeration stage, it goes to our secondary clarifiers, which are functionally identical to the primary clarifiers. But at this point, we're not just letting the pollutants don't settle out on their own. What we do is we limit the food, and without any new pollution coming in, these bacteria and protozoans, they just kind of grab on to, they eat as much as they can and they grab on to what's left. And they just sink to the bottom of the tank. They go dormant. So at that point, we are drying off those solids to our solids handling process, but we also utilize a portion of those solids to reseed the aeration and bioreactor phases. That way we can ensure that we always have a nice healthy population of bacteria, and we don't, because you need a lot of them, to do this. So this is a picture, this is a schematic of our East plant secondary process. We have 4 separate open top tanks that we're adding the oxygen to, where the hard work is happening with the microorganisms, and we have 2 final clarifiers. I wished I could have had more pictures, but I was able to get pictures of these to share with you so you understand what they look like. So I'm standing where the person that took this photo was not me, but they're standing kind of with their back to River Avenue, looking east. And this is one of the 4 bioreactors, or we call this East reactor. That mixer is actually floating in the center, and there's a propeller on the bottom of it. And that mixer is taking oxygen, which is fed to it through this green line, and it's mixing it in, and it's telling it to, it's allowing it to eat away on the pollutants that are there. So once we're through with that part, we're going to the secondary clarifier, which this is a picture of one of our, and we have 6 secondary clarifiers, and they all are basically the same thing. And it is hard to tell. It looks kind of brown in here, and that's because all those bacteria and the microorganisms are in the water, but they're settling down, working their way down, and the clarified water off to the side is clear, especially unless we're having a bad day, that water is gonna be really nice and clean and clear and ready to go out. So we're, 90+% treated at this point. So the west plant is very similar to the east plant. It just uses a different tank technology. These reactors 1 through 5 are actually enclosed tanks, but they do the same exact thing as the reactors that I just showed you. And we have 4 final clarifiers on the west side of the road. So that allows us to treat, we can do more treatment on the west side of the road than we can on the east side. So we do about 2/3 of our treatment with the west plant and about 1/3 with the east. We do have the ability to generate oxygen, and that's a pretty neat process. We're basically taking air and we're scrubbing out the nitrogen, and whatever oxygen is left is then going to the reactors. The rest of our oxygen is supplied by Praxair. And Praxair generates oxygen in Detroit and the East Chicago area. So we get trucks in, every few days of deliveries. So after we've done our secondary treatment of both sides of the road, we are disinfecting. And this is what's eliminating the human pathogens that may be left in the wastewater. So all the solids are already gone. The BOD has been treated. We're now disinfecting, and we use sodium hypochlorite bleach. We used ozone at one point in the past, but what we're doing here is just like when you're disinfecting something at home, we're just trying to kill any sort of human pathogen. And that's why we're tracking the fecal coliform bacteria. So not only do we add the sodium or hypochlorite or bleach, which is at about 15% strength, that we let it sit for a minimum of 15 minutes, kills the coliform, kills E. coli, all of that. Then we have to use a sodium bisulfite, which removes the bleach from the water, and then it's safe to be discharged out into Lake Macatawa. This is a simple schematic of what that tank looks like. It has 2 trains, a north and a south part. We add the sodium hypochlorite to the flow that comes off of our east plant and west plant secondary clarifiers. And then we add the sodium bisulfite rate at the end before it goes out to Lake Macatawa. We do have a reclaimed water system, which we can't sell the water to be reused out in the public, but we are able to reuse this water on our site. So all of our irrigation water inside of our fence is actually treated wastewater effluent, and we also use it for a lot of our processed water. If you go down to like Florida is a good example, or the Southwest where water is very scarce and expensive, a water reclamation facility will actually pump their treated wastewater to golf courses, industries to use for cooling water. There's lots of uses for it. They generally are treating to a higher standard than what we do, but it can be done. And actually, there are some that discharge their wastewater effluent into their drinking water reservoirs, if you would believe that. Because at this point, it is basically just water. It just needs to be filtered and chlorinated, and it's ready to go back into the drinking water systems for people to use. So now that's the liquid process, our first output. That's honestly the easiest output of the 2. The next part I'm going to focus on for a little bit is the biosolids portion. And our biosolids go to 2 different uses right now. And one is actually just landfill disposal. It's not even a use. And the other goes to land application. So for the landfill, we are dewatering the solids. So when we pump the settled solids from our primary and secondary clarifiers, they are, anywhere between 1/2 to 1.5% total solids. So that means that the rest of it is water. So they're like 99% water or so. We can treat the water. We need to separate that from the biosolids. So what we do for the landfill is we actually dewater the solids, and dewatering is done through a screw press. And the screw press that we have, there's a schematic of one shown in your upper part of the slide. And basically the sludge and solids, you hear those kind of interchangeably. We try to move away from sludge, but it is an industry term that comes into the screw, and the screw presses. It gets closer together as the flights go on, and it pushes the solids together, and it forces the water away from it. The water comes out along the screen, and then is discharged back to the plant where we can treat it and then send it out to Lake Makatawa. The solids are, there's a picture here of what dewatered solids look like in the center, are loaded into dumpsters, and then they go to a landfill for disposal. These solids are about 25% total solids, so you're still at 75% water, but without doing any sort of thermal or drying process, that's about as dry as we can get them. This is a schematic of what our current process is. So we're dewatering primary, we dewater our waste activated sludge from our primary and secondary clarifiers in the screw press, and we send them to a landfill. I was able to get over and grab a picture of our screw presses. So these are pretty nice units. They're about 25 feet long or so, now 6-7 feet tall, something like that. And the process, actually the solids enter on that box on the upper left, and they travel through the screen to the right towards this motor and gearbox that you'll see in blue. And we've removed all of the panels from the side of this. Normally this inner barrel would not be visible, but when it's running, water will shoot out of it. So that's why you have to have covers. That is a perforated screen. So that allows the water to go out, but not the solids. For land application, which is a beneficial reuse that I'll speak more of here soon, is a way to utilize the fertilizing properties of the wastewater, plant biosolids to grow crops. There are many different things you can do with biosolids for beneficial reuse, but we focus on right now, what we do is land application. And we use we have a contractor that shows up, they haul away our biosolids, and they use one of these terrigators, they're called, to inject the biosolids into agricultural fields. Basically, it's pumped into this tanker, and then there's the hoses you can see going down to these plows. And the plow opens up the ground, you discharge the biosolids under the ground, and it closes back up. That helps limit any runoff concerns or odor concerns when they are land applying. This is just an general overview of what the process is. So from our secondary clarifiers, and we do take some primary clarifiers, the solids off the bottom go to the gravity belt thickener, which then thickens the solids to about 5.5% total solids. So 95 or so % water. And we put it in our sludge storage tanks. At that point, we add lime to them to stabilize and kill off pathogens. And then the hauler takes it and applies it on the land. I grabbed some pictures of the gravity belt thickener. This hopefully will help you understand how it works, but the picture on the right is one in action. You can see the water coming out the bottom of the PVC pipes, and the flow goes on this from right to left across the picture. That picture on the bottom left is a close-up of the belt. So this doesn't have any solids on it. It is our machine that we just cleaned. So you can see there's this flexible fabric belt. And as the solids ride across, it hits all of these fences and it flips over. The solids flip, and the water via gravity will go through the fabric, and the solids will stay on the top. So that's the way that we can it's a very quick, easy, efficient, fairly affordable way to separate solids and liquid in the wastewater process. So some of you may have seen a talk I did about a week or so ago on the biosolids, and these are some slides I pulled from there because I want to help you understand what they are. They're a hot topic item. They always have been. I think they always will be, to be honest with you, and the steps that we do to keep these biosolids safe. So the biosolid, the water sides, like I said, is easy. The biosolids are defined by EPA as solid, semi-solid, or liquid residue generated during the treatment of sewage in a treatment works. I pulled that right off of the EPA's website. They had a couple different versions. Generally, there's three components: the primary and secondary solids that I told you about earlier, and then the FOG, which stands for fats, oils, and greases, which are pulled off of our primary clarifiers. Generally, across the country, you're going to see these three end uses for biosolids. You have land application, which we are currently doing here in Holland, landfilling, which we also currently do, and then incineration. And actually, we did incinerate at one time back in the 1960s. It didn't go very well, and it was abandoned, I think, after only about 5 years or so. Biosolids safety is always something that is brought up because yes, biosolids are all the solid portions that aren't treated as water are biosolids. So there's things that you need to keep an eye on. We have to keep an eye on the nutrients in the biosolids. That's a big part of it. We can't overload the agricultural fields. We don't want to cause any sort of runoff that makes its way into the watershed because that could cause algal blooms. You can poison the water. You don't want to have any sort of vector being spread. So we spend a lot of time and a lot of money making sure that's land applied right and that we have it well monitored properly. The part I was discussing earlier, our pollution, industrial pollution prevention or pretreatment program, our IPP guys, they're the ones that are really play a pivotal role in keeping toxic chemicals out of our biosolids. So heavy metals are a big one. The PFAS, PFOA is a big one. And we also treat them there's Class A and Class B standards that are set up by EPA for human pathogens that we will treat to make sure that these biosolids are safe. As I said earlier, we're using lime right now. We treat to a Class B standard. And then once our new digesters put in, we'll be treating to a Class A standard. There are rules, there's regulations to all of this. A lot of this comes from the Clean Water Act. There's 40 CFR Part 503, and then there's Part 258 on the federal side. And the state of Michigan has the Natural Resources and Environmental Protection Act of 1994. Those are really kind of what guide and dictate what we can do with our solids to beneficially reuse them or to send them to a landfill. As part of those rules and regulations, we and any other wastewater treatment facility that beneficially reuses their biosolids have to have a residuals management program. We developed this using EPA guidelines, and we have it approved by EGLE, and that outlines how we treat our biosolids, how we land apply our biosolids, what we're doing to monitor them, making sure that we have the right classification. Something you'll hear me talk about a bit here is vector attraction reduction. That actually is referring to vectors as in like flies or rats or mice. Anything that could potentially spread disease to other, maybe it could take it from a field and spread it to a community, which we don't want to do. So that's all a big part of the treatment process. And as part of that, to go a little bit more in depth in the classification of biosolids, the EPA set these rules up many years ago to ensure that we have safe and identifiable methods that we can treat our biosolids with to reduce risk of human health issues. So that vector attraction is a big part of it. That's why we subsurface inject our biosolids. Anaerobic digesting helps with that as well. It eats up all the tasty parts, so the flies and the rats and mice have no interest in it. The Class A biosolids are, I'll show you some examples of those, but they can be used for many different applications. You can use them as soil amendments. You can use them as fertilizer. They're a clean product. They've been proven to have very, very minimal amounts of any sort of vectors or pathogens. Class B do have more, and that's what we have currently. And that's why we have to be very careful about where we land apply them and when we land apply them, because we use site management practices along with lime stabilization to ensure that there's no risk to human health. So for the Class A biosolids products, the most famous one, especially in this region, would be the center of the milorganite. Milorganite is sold pretty much any gardening center. You can get it at Lowe's, Home Depot, Menards. And milorganite is a Class A biosolids product that comes from Milwaukee, Wisconsin, from their wastewater treatment facilities. And they've been producing this since, I believe it's like 1919. It's a very, very long time. And it's been proven to be safe, used a lot in golf courses. City of Chicago has a Class A biosolids product they call EQ Compost. They just use it locally there in the Chicago area. Washington, D.C., they have one that they call Bloom. You do some searching online, you'll find there are many examples around of products that are either sold or just given away that can be used for soil amendment properties and adding organic matter to soil, not just the nutrients. Speaking of the nutrients, was used as a fertilizer, so NP and K, nitrogen, phosphorus, potassium are all present. So whatever we land apply, we track not only what the nutrient levels of the soil of the field are, but we need to know what crop is being grown on it and how much of the nutrients is that crop going to use. Because corn uses so much nitrogen, so much phosphorus. Well, if we keep applying more than what the corn is going to use, eventually the field will meet a saturation limit, and those nutrients will run off into the watershed, and we certainly don't want that. Heavy metals are a big one because they bioaccumulate. So that's we test for the following: arsenic, cadmium, copper, lead, mercury, nickel, selenium, and zinc. EPA has some set limits that those need to be under, and we're fortunate that we're well under all of those. If we were to ever have an issue with heavy metals in our biosolids, we would handle that through the IPP pollution prevention program. PFAS is what we call a emerging contaminant, and that is, that was similar. Mercury was one, probably 20 some years ago that we had to work our way through. And PFAS is the one that we're dealing with now. PFAS, I'm sure most of you are aware of it, it's a pretty hot button item, but if you're not, it was like Scotch Guard. It's used for anti-stick. They use it for anti-foaming agents and metal finishing for chrome platers. And unfortunately, it's incredibly pervasive in the environment. It's everywhere. So even if we test our domestic wastewater coming in just from households, there are small amounts of PFAS chemicals in it. So we're working very closely with Eagle on this as we move forward. We are testing our effluent, as I showed in our permit earlier, twice a year. We're testing our biosolids. We don't have to test them yet, but we want to test them because we want to know what's there. We also have been testing our customers that discharge to us as well. We did identify 4 customers, and we've been able to work with pretty much all of those customers to eliminate the PFAS coming to us. So we're very fortunate. And you hear some horror stories out there. I think like Kalamazoo had issues, Lapeer. We never were in their boat even to start with, and we have some really great industries in our town that have stepped up to help clean up any little bits that are coming to us. So we do continue to track it, certainly not going away, and we're only going to, become more strict with these chemicals going forward. There isn't a set limit of PFAS that can be discharged in biosolids or even in the liquid right now. We try and keep our liquid underneath the surface water quality standards, which for PFOS is 12 parts per trillion and PFOA is 12,000 parts per trillion. For biosolids, the best we have is the Eagle has identified 150 parts per billion, different from trillion, as the threshold for industrial impacted biosolids. Our results I've listed below. For our PFOA, we had a non-detect, so our detection limit was 0.496 parts per billion, and our PFOS was 6.95 parts per billion. Best we can do is really compare ourselves to other wastewater plants around the state, and we are looking pretty good. So we continue to tackle that through our pollution control program, and someday we hope that there can be no PFAS anywhere. That'll be the goal. So I've clouded your mind with a whole bunch of information. We've had the history, we've had how the plant works, what we're doing with our biosolids, and I want to go from the biosolids to really probably the most interesting thing in my day every day, and hopefully some of you will be interested in this as well, is our anaerobic digester project that we're doing currently at the Water Reclamation Facility. If any of you have been down to Window on the waterfront lately, you'll notice there's some demolition going on, some old tanks being removed. We're in the process of building one of these anaerobic digesters. I have a picture of 2 that will be similar to what we're going to end up with. The pretty nice sky blue, robin's egg blue egg, you want to call it, on the left is from Hershey, Pennsylvania. And the one on the right is from right down the road in Granville. So you can actually see the top of this digester when you're going down 196 heading towards Grand Rapids. The question is, we had an anaerobic digester back in the 60s. We moved away from it. So why go back? Why should we do this? Well, we're always trying to be sustainable. We're trying to have a process that best serves our customers. And the biosolids have been very high risk. and they have been forever. You know, I've two superintendents ago, he still emails me just nightmares, you know, of the biosolids issues they've had to deal with in the past. We have three large risks to our disposal, I'll call it, of biosolids, and those are landfill limitations, storage limitations, and land application limitations. The landfill limitation really is that they don't want as much of our dewatered solids as they used to take. Matter of fact, we've been cut down by like almost 50% by the landfill we're currently using. And that's because these solids are still 75% water. That means that they do shift, they do flow. So you need to mix these biosolids with municipal solid waste, like what might come from your house, in order to make it set in a cell properly. You know, it's a great thing, I think, but recycling has done wonders, you know, and composting. There's a lot of waste diversion efforts out there, and they're working. Unfortunately for the people in the wastewater industry, that means there's less of the municipal solid waste to mix with your dewatered biosolids products. So that's a big limitation there. This site-specific issue, we have storage limitations, that our storage tanks built back in the mid-1990s are not as big as they need to be. Really, we're at about 40% of the storage we should have. And then land application, given it's a Class B product and we're land applying it safely, we can land apply in winter. We can't land apply when it's raining. You know, we have setbacks from houses, setbacks from wells. So there's a lot of limitations on the land application side of it as well. So all of those together are high risk. And what does high risk mean? High cost. So our landfill disposal costs it's an astronomical increase. You know, I started tracking this we're in 2008 to now, it's gone up by over 600%. It's really hard to budget for a 600% increase, and we don't know where they're going from here. You know, land application is more affordable, but it's still gone up 65%. So we needed to do something, you know, so we can continue to serve our customers. And so that's kind of what led into this project. So BPW, you know, we wanted to look into how are we approaching this project. We want to look at this holistically. We want to look at it sustainably. So, you know, what do we want? We would love to reduce the volume of our biosolids. We'd like to produce green energy, Class A biosolids. We want to do something that's not only just cost effective, but environmentally friendly as well. So that's what brought us towards the Envision design principles. That, for any of you that are familiar with the Holland Energy Park project, that was done under Envision design principles as well. And I have a little bit on that next. So Envision kind of means that we're looking at things holistically. We're following a sustainable outlook. And as part of that, we decided, well, maybe we should apply for state revolving fund money. That's money, a low interest loan or bond, you know, basically it's EPA money managed by the state of Michigan. And they will give you money back if you're doing something that's environmentally innovative. And we're very fortunate. They gave us $6 million to help pay for this project. So, you know, to me, that really vindicates that we're doing something that's environmentally friendly and sustainable. You know, we need to bring the community into this. So we've been working with Outdoor Discovery Center. We've been working with the Holland City, you know, Parks Department. So we want to work on having interpretive site signage around the facility. Someday, when people can visit again, we'll continue to have tours like we always had. You know, we want to work to make sure that we're going to fit in with Waterfront Holland visioning, as we're a key part of it. You know, for some people, like it or not, that it's not going to be easy to get this plant relocated from where it is right now. For those unfamiliar with Envision, it's a process kind of like LEED for infrastructure is how I like to describe it. Provides consensus-based framework for assessing sustainability and resilience in infrastructure. And this Institute for Sustainable Infrastructure is a combination of several different groups. We have the American Public Works Association, American Society of Civil Engineers, American Council of Engineering Companies, Harvard Graduate School of Design, and ZOFNAS program for sustainable infrastructure. And it really wants us as utilities to do things that are sustainable and equitable for the communities in which we work. So our goal on this, there are several different phases from, you can be Envision verified, silver, gold, platinum. So we're hoping to get gold. So we're aiming pretty high with this project, and I think we'll be able to make it. So we've decided what we need to do. We decided we need to do something first. Now, what are we going to do? In 2015, we replaced our solids handling equipment. In 2018, that's when we decided we need to do something further. So that's where the alternative analysis came in. So we looked at several different options for disposal, not just anaerobic digester. We looked at expanding our storage. We looked at doing thermal drying to make like a powdery product. We looked at some different types of anaerobic digesters. And we decided after looking at the numbers that it made the most sense to move forward and look at digesters, but also look at additional storage. So in 2019, we did a pilot study, partnered with Kettering University, who runs miniature digesters in their lab, and we did a conceptual design. For those of you who are curious what a little miniature lab digester looks like, here's a picture from Kettering, and there's 4 different small carboys there, and each one of those is being mixed constantly and heated, and it's producing biogas, and they're catching it in these plastic bags that are attached to it, and that allowed us to understand if we can digest, which we could, and that it actually looked like it worked really well for us. So from all of those steps that we took coming up to now, we determined, yes, digester is the way to go. It's going to reduce our volume of biosolids because it actually converts them into a gas form that's rich in methane. And we're going to make a Class A biosolid because it's going to give us more options for what we can do with it after the digester. We're not going to have to do lime stabilization anymore. This will be an integral part of our plant that we can, design around into the future. An anaerobic digester is really nothing more than an enclosed tank with no air in it. There's no oxygen, hence anaerobic. It has different bacteria, anaerobic bacteria, and the tank is mixed. This is a picture I took off the EPA website for a manure digester, but I thought it got the point across quite well. So you mix what's in the inside of the digester, the anaerobic microbes break down the solids and they produce biogas, which we collect at the top. And that biogas is 60% methane. So it also was a great thing. We're going to be able to remove like 40 to 50% of our biosolids through this process and turn it into a usable product, which is the biogas. We've chosen to go with an egg-shaped digester, which I showed pictures of at the beginning. And an egg-shaped digester really just means that the insides of the tank are all rounded and it's completely round. There's no square corners or anything. And that provides better mixing and it provides less places for the solids to depose into. So the corners of a normal flat bottom tank, solids will settle down and they'll stay on the bottom and you have to clean them every so many years. It's a very odorous process. And we've proven that they've been able to run these digesters. We've talked to people who have been running them for 20, 25 years even, and haven't had to clean them. And when they have emptied them, they've been like in perfect condition. So for us, it just makes great sense. We are going to utilize the biogas for cogeneration of electricity and heat. So our goal is 550 kilowatts of renewable power. So that should power over half of our plant. And we're also going to use the heat not only to heat the digester process, but to heat the buildings as well around it. So it's a really nice project. Just for your information as to how this is going to fit in the process is we have, this is an updated schematic of our plant process with adding the digester. So you've seen 1 through 6, we walk through the influent, the headworks, the primaries, the aeration, secondaries, and then disinfection. But on number 7 and 8 and 9 here, this is where we're going to pull off those solids off the primary clarifier and the secondary clarifier, and we're going to digest them in the digester. The biogas will be burned for electricity and heat. And then the solids are going to be aerobically digested. So we're going to add air to them and oxygen, and that will treat the ammonia that's generated in the process to make sure that we have an effluent that's safe for the environment. So that's really the process of it, and then we were looking into, okay, what are the costs associated with this? So it's not cheap to add anaerobic digestion. We're looking at The total capital cost is going to be $33,700,000. You should note that that is before we are able to subtract $6 million from that due to the Green Project Reserve through the state of Michigan. So really that's a big portion of the project that we're able to get covered. So we're very happy about that. So in Holland, we always want to make sure that we are doing not only what's environmentally sustainable, but we need to be doing something that is also economically sustainable. So we run net present value calculations of all the project expenses. So that includes operations, maintenance, equipment replacement, chemicals, electricity, everything that we can think of, we put in there to try and give us a good idea of what's this going to cost to run. And so on average, we've been seeing about 7% per year disposal escalation on our biosolids disposal costs. So we projected that out for 20 years. And we wanted to compare not only what the digester costs, but what would happen if we just simply built a bigger storage tank and still land applied. Also, what would it cost if we did nothing? Unfortunately, we really can't do nothing, but this shows that it actually is cheaper for us to add the anaerobic digester. And we're looking at a $59.8 million as compared to $70 or $75 million. So that's an all-in cost for 20 years. The beauty also is after 20 years, you don't have to, all the capital is paid off at that point. So it becomes even more affordable to utilize this process. The big cost savings you see come from the power and heat generation, but also because we're reducing the volume of solids. So we're getting half of those solids taken care of right on our plants, less trucking, less disposal costs, and such. So we also wanted to take a look and present, we've presented this around a few times. You may have seen it before. It's been in the Holland Sentinel, is what is this digester going to look like? We are very close to downtown. We understand that there's parks near us, there are condos near us. We're not trying to hide anything. We're just trying to do it. We're trying to do what we do in the best way possible to help the community out. So we had one of our engineers put together some conceptual layouts of what the digester is going to be. These are from an earlier iteration in the design, so it doesn't look exactly like this, but the tank will be the same. So the gray rounded portion is the anaerobic digester. It's 102 feet tall from the ground to the very top, but that structure on the left side of the tank is actually a stair tower. And rather than having that stair tower, which is even taller, we will have stairs that actually wrap up the side of the tank itself. So this is the most visible part of it right here. So we're standing here on the south side of the plant, Central Avenue, looking north towards 3rd Street, and you can definitely tell it's there. And then I went for a bit of walking on this day, and I walked all the way up to the River Avenue Bridge, and I took a picture looking south. So now you can see on the right side of this photograph is the James DeYoung Power Plant, and then on the left side, poking out from the trees, you can see the anaerobic digester. We certainly want to be cognizant of our customers on the north side of the river. So I actually continued my walk all the way around to River Hills Drive, so back behind the D&W. And I stood by a lift station we have there, and I took a picture looking south. So this is across the river. So you can see the digesters on the left, and the James DeYoung plant is on the right. And the last one, which is always very important, as we understand, is how's it going to look from Windmill Island? So I climbed up on the, in the parking lot, there is a observation platform. So I got up as high as I could and I took a picture, and this was a day after most of the leaves were down. So you can see about as good as you're gonna be able to see. And I'll be honest, it's even hard for me to look at it. You almost need to zoom in, but that's Freedom Village on the left. And maybe a third of the way from the right, you can see the little stair tower sticking up, and to the right of that is the egg. It's directly to the left of the James DeYoung smokestacks, which are visible. To me, that's great news, because for those that are afraid maybe it would sully the view from Windmill Island, during the summer when most of our visitors are here, you'll have a lot of nice foliage on those trees, so it should be green. You shouldn't really notice. I will throw out there that when we did the drawings, we picked gray, but there's really no reason the digester tank needs to be gray. So we've got a few different, that's something that will be a part of the discussion going forward, is what it's going to look like. This is another early schematic of what the plant would look like, looking eastward towards the digester. So the demolition has already started. It's going to be about a 3-year project, so I expect to have this digester online in May of 2023, and we're definitely looking forward to it. So I believe that is the end of my presentation, and want to entertain any questions. And thank you for sticking with me. It's a lot of information.
That was great, Theo. Thank you so much. I wanted to say before people start verbally asking questions, there are about 6 questions in the chat, and some of them may have we're a little bit beyond that. I hesitated interrupting during, but do you want me to go through the written questions kind of quickly and then leave some time for dialogue?
Sounds great to me.
Okay, first question that came in right about at the beginning of your presentation. Are you near capacity typically, or is there excess capacity still?
There is excess capacity. If we ever get to a point where we're normally over 80% of our capacity, we have to be thinking about the next expansion. If we're over 90%, then we actually need to be physically planning for it. So it's something we always keep our eye on. It seems like this area, it always surprises us in a good way that it continues to grow. During the last recession, it maybe only set us back a couple of years, but we still had to expand the plant before we thought we would. So.
Okay, thank you. This, I heard a little bit of you answering this, but what are we putting down the drain that we shouldn't?
Yep, so definitely the flushable wipes and kitchen grease are 2 really big ones I can think of. Also I would like to just go out there and say anything that is plastic, please don't flush down. We get a lot of put it lightly, feminine hygiene products end up their way down here. So, really the right place for those is the trash. They plug pumps. We have operators and maintenance workers that have to physically pull them out of pumps. If they don't, end up in the trash, and then they end up in the garbage anyway. So those are big ones. There's things that always surprise me. We put toy cars, but sometimes it's hard to stop your kid, from dunking one of those down the toilet. So yeah, just think about it, and I'm not personally anti-garbage disposals. I know a lot of plumbers are, and I've had that happen to my house too, where it's backed up. Just be careful that it's not grease and fat that you're putting down the drain to us. And so that's a lot of, also another big one I should throw out are pharmaceuticals. Our plant doesn't treat pharmaceutical waste. So if you dump it down the drain, it just goes right on through to the lake. So thanks for that question. I should have thrown that in the presentation.
Well, great, because that was a question too from right now, and that's important to know. I mean, I think that there's a big initiative to just get prescription drugs taken care of responsibly, regardless.
Yeah. Yep, and our pollutant control program works with that a lot, and so you can go to like the police department and drop them off there, or at most pharmacies as well, if you want to drop off your drugs.
Okay. Thank you. How much clearer is commercially filtered water compared with what BPW provides in our homes? What about fluoride additives? And how much has BPW been impacted by federal EPA administrative decisions to cut back on services?
Sure, that's a few different parts there. So we do add fluoride to our water. We have for a long time. We don't do it here. That's at our water treatment plant out near Tunnel Park. We've been doing it. I think Grand Rapids was the first city in the country, and we weren't too far behind them. So that is done on the water side. So what we're sending out of our water treatment plant is perfectly safe. It is beautifully clear. We have a very dedicated staff there. Nate Johnson's their superintendent, a lot of operators. They have sand, gravel filtration, chlorination. Those are some guys that really take their job seriously. So I have no qualms, honestly, with any municipal water. So on the Holland Township, they get theirs from Wyoming. It's an excellently run plant. Where I live, my water actually comes from the city of Grand Rapids. So, there's a lot of very dedicated people out there. So I want you to know you can trust that water, and that there's a lot of people paying a lot of attention to it. So I think there's a question, part of that was about the EPA cutbacks. We are seeing some of that mostly in delayed turnaround time for clarifications on regulations. And PFAS is an area we're kind of waiting on because we have tests for PFAS but they're not actually approved for wastewater. So while we think it's right, we don't really know. And that's something for EPA to do. So we are certainly waiting on that. But generally, Eagle's been great. We're working with them every day. They're doing everything they can to ensure that we're able to provide safe treatment to the sewage coming to us. Was there another part in there that I missed?
I think you actually hit all 3 points. How much clearer is commercially filled water compared to that of BPW, fluoride, and the EPA?
Yeah, and I would say what you're getting from like Culligan, I personally don't think there's any difference to it. There is if you want to have like RO water, yes, that is more in-depthly treated than what we do. But I don't think that I could tell any difference myself personally.
Okay. Then the last question in the chat before we open it up to verbal questions is the biodigester at Lowell got a bad review for odor. What is the difference about the Holland system?
The Holland system is a fully enclosed tank. There's actually a lot of things that were done, in my opinion, wrong at Lowell, but our tank is fully enclosed. There's no cover to separate or to tear. The Lowell tank was actually also built to receive a lot of very high strength waste. There's a salad dressing manufacturer out there, and the Lowell wastewater treatment plant is not very big. So every time they would get a slug load from this salad dressing company, it would overload their digester. I also have been told there were some other things that like open reception pits. We would never do that here because it provides a lot of odor potential. And trust me, odor is something that I wake up and think about at least several times a week. It's pretty serious business here in Holland, given the downtown. So yes, we
have different worries with our jobs, right?
Right. So I hope that helps to answer some of those questions about Lowell, but we certainly have been kept in tight on that project because I used to actually work with some different digesters before I even worked at Holland. So.
Okay. Another question came in the chat. Why is it that water tastes so different from community to community?
I think generally it's your source water. So a lot of times, I don't personally notice a difference between City of Wyoming's water, City of Grand Rapids water, and City of Holland's water. But I grew up in Eaton Rapids, Michigan, over by Lansing, and we have aquifer well supply. And that you definitely get a difference, mostly due to hardness. Other things that could cause differences in taste might be, it could be I'm just trying to think exactly. A lot of it comes down to also how much chlorine they add. Some plants have to do more than others in certain areas. So I will notice sometimes coming out of my tap, it might be a little bleachy. Usually if I let it set, that goes away.
I don't see anything else in the chat. So if somebody has an additional comment or question, by all means, just open up, unmute yourself and ask away.
I'm impressed by the total number of flushable things that went through your system. And you also talk about regulating industries. How can that be regulated? I mean, obviously it's a problem for you. Is it a problem for everybody?
It is. It can be, definitely. We have an ordinance and we have an entire pollution control program department, but smaller cities especially may not have the same ordinances necessary to protect their wastewater systems. So we work with Eagle. They have their rules, so they give us our permit, and then we write our permits to match what our permit says, basically. So that's how it's kind of passed along. So it passes down through the Clean Water Act authority to the state, to us, and that's what gives us the authority to write our own city ordinance, which then allows us to regulate our customers that are discharging to us.
So basically in Holland, you're not supposed to flush diapers.
Well, I mean, we can't really control that, but we ask people not to very nicely. We really only have the ability to control, like an industrial customer. So we do work with, one like Holland Hospital would be a good example. Someone we've worked with in the past. They used to flush a lot of unbiodegradable materials to us. And they weren't doing it maliciously, they just didn't understand the issues it caused. So, you know, we worked with them to help them understand what can come to us. So Freedom Village will be another example of people we've worked with in the past to help reduce inorganic material coming down to us. Same with the pharmaceuticals, you know, we can ask, but outside of any, like a large facility, like a Freedom Village or a Holland hospital, we're not gonna come to someone's house and, you know, try and shut off their water because they flushed a diaper to us. And Susan, you're muted.
Susan, you're muted.
Sorry, thank you. What other gases are present in biogas other than methane?
It's 60 to 65% methane, and pretty much the rest is all carbon dioxide. There are maybe some trace amounts of nitrogen, and there also is hydrogen sulfide present, but we do scrub that out before it gets utilized. So because hydrogen sulfide is toxic and it's also really corrosive to equipment. So we have some scrubbers that will be installed as part of this project.
Great. So we are right almost at 2:30. If somebody has a last question, go ahead and ask. Otherwise, we'll wrap the class.
Wonderful. Well, you know, certainly for anyone, once COVID is back under control, if you ever want to come out and visit, we're happy to show people around and would love to have you. But if anybody comes up with any of your questions, feel free. My email address is there, and I'll be happy to follow up.
Well, thank you on behalf of HASP and everyone here. Thank you so much. We appreciate, that was amazing content, very informative. And thanks, Kay, for coordinating the class. So if there's nothing further, I'll go ahead and close out.
I do have a question, Susan.
Yes.
This is Louis Morel. Regarding the micro testing, do you have the lab test for total E. coli or only certain species of E. coli, since some are not pathogenic?
Right. We look for fecal coliform as an indicator of bacteria. So, you know, we can actually test for E. coli if we needed to, but we really just track the fecal numbers, because that gives us the indication to understand whether or not there are the chance for E. coli pathogens to be. So yeah, so you are correct. What we're actually looking for is not pathogenic, the coliform bacteria in itself.
Okay, and along those lines, I had another question. Oh yes, speaking of bacteria, in the aerobic process that you have now, do you simply use bacteria that are present in the air, or do you actually seed with desirable bacteria?
The bacteria we have cultivated at the site actually all come from every one of us. So it's more or less cultivating the gut biome that comes in with the you know, fecal matter, and then we continue to recycle that in the plant. So we're only getting rid of so much of it every day, and we cycle those bacteria back into the bioreactors to allow them to keep doing their work as long as possible.
Okay, and how will you then add the anaerobic bacteria at some point?
Sure. So what we will do is we will reach out to Granville is a perfect example, and they can give us a couple of like semi-tankers loads of their biosolids, and theirs will be rich in the anaerobic bacteria. So we can grow them ourselves, but it takes a long period. So if you start a digester from scratch, it's going to take you, you know, months to a year. If we go, say, to Granville as an example and grab 30,000 gallons of theirs, it's going to fire up right away, and those anaerobics will take over.
Right, I get it. Okay, thank you.
Oh, thank you.
Well, again, we just thank you so much for all the great information, all the work you're doing in the community to keep us safe and keep things running. So with that, everybody have a wonderful afternoon. And Theo, if you have any reason to talk to me after class, we can stay on. Otherwise, farewell.
All right, thanks. All right, nice talking to everyone. Bye.
Great. Bye, everyone.